Welcome back to the Null Pointer, and today we'll go into the realm of software design principles, especially the
solid principles.
Before we go into the principles themselves, let's take a step back and see why they're so significant in the programming world. SOLID stands for 5 important concepts that assist us in writing clean, manageable, and extendable code. Robert C. Martin, often known as Uncle Bob, proposed these ideas, which have since become a cornerstone in current software development processes. These principles are Single Responsibility Principle, Open-Closed Principle, Liskov Substitution Principle, Interface Segregation Principle, Dependency Inversion Principle. Let's start with an overview of each principle. Single Responsibility Principle, SRP. A class should have only one reason to change, meaning it should have a single responsibility. This principle helps us keep our code focused and prevents it from becoming overly complex. Open-Closed Principle, OCP. Software entities should be open for extension but closed for modification. In other words, we should strive to design our code in a way that allows us to add new functionality without modifying existing code. Liskov Substitution Principle, LSP. Subtypes must be substitutable for their base types without affecting the correctness of the program. In simpler terms, this principle ensures that we can use derived classes interchangeably with their base classes. Interface Segregation Principle, ISP. Clients should not be forced to depend on interfaces they do not use. This principle encourages us to create fine-grained interfaces that are tailored to specific client requirements, avoiding bloated interfaces that lead to unnecessary dependencies. Dependency Inversion Principle, DIPP. High-level modules should not depend on low-level modules. Both should depend on abstractions. This principle promotes loose coupling and emphasizes the importance of coding to interfaces rather than concrete implementations. Let us now examine each premise in further depth, beginning with the Single Responsibility Principle. Assume you have a class named Order that manages both the generation and persistence of orders in a database. Because it has 2 obligations, this is a violation of the single responsibility. It's a good idea to divide such functionality into separate objects. We make our code more modular and easier to maintain by splitting the concerns. Each class now has a single duty, and any modifications in one area will have no effect on the other. Moving on to the open-closed principle. Let's say we have a class called Payment Processor with a method called Process Payment. If we need to add support for a new payment method, we would traditionally modify this class, potentially breaking existing functionality. However, with the open-closed principle, we aim to extend rather than modify existing code. By creating separate classes for each payment method that inherit from the payment processor base class, we can extend the functionality without modifying the existing code. Now let's move on to the Liskov Substitution Principle, which states that derived classes should be substitutable for their base classes without causing any issues. In other terms, if a method works with an instance of a base class, it should also work with any derived class without breaking the program's correctness. In this example, the square class inherits from the rectangle class. However, by violating the Liskov substitution principle, we end up with unexpected behavior. For instance, if we set the width of a rectangle to 5 and the height to 10, we expect the area to be 50. But when we apply the same logic to a square, we get an incorrect result due to the principle's violation. Here's how you could implement same logic without breaking Liskov substitution principle. Next up, we have the interface segregation principle. The interface segregation principle states that clients should not be forced to depend on interfaces they don't use. Instead of having large, monolithic interfaces, it's better to create smaller, focused ones. Let's take a look. By separating the printing functionality into its own interface, we allow clients to depend only on what they need. This promotes cleaner code and reduces unnecessary dependencies. Lastly, we have the dependency inversion principle. The dependency inversion principle encourages us to depend on abstractions rather than concrete implementations. By doing so, we achieve loose coupling between components and make our code more flexible. By passing the payment processor instance through the constructor of the order class, we invert the dependency. Now, the order class depends on the abstraction, the payment processor interface, rather than the concrete implementation. This allows us to easily switch the payment processor implementation without modifying the order class. Dependency inversion principle can also be referred as an inversion of control or dependency injection. All of these principles can be found in many popular and widely used frameworks, like Spring for Java, Django in Python, or Symfony in PHP. If you ever use some of those frameworks in your journey, you will most likely encounter these principles being used. And that concludes our video on solid principles. We've covered the basics of each principle and provided some TypeScript code examples to help you understand its implementation. Remember that incorporating these principles into your coding practices will result in cleaner and more maintainable code. If you found this video helpful, be sure to give it a like and subscribe to our channel for more programming content. Also, don't forget to turn on the notification bell so you don't miss any updates. As always, thanks for watching and happy coding.